Hello everyone, Mehdi Mortazavi here with another video on engineering thermodynamics. So today I'm going to talk about the Clapeyron equation. Basically, in Clapeyron equation, we are utilizing one of the Maxwell relations that we discussed earlier. So we had four Maxwell relations. We discussed about that in a previous video. And today I'm going to work on the first equation that we had in Maxwell relations. So the title is the Clapeyron equation, and the Maxwell relation that we had before said partial P partial T when specific volume is constant is equal to partial S partial V when the temperature is constant. Okay, so during the phase change process, we know that the saturation pressure is a function of saturation temperature. Okay, so we know that during the phase change, P sat is a function of T sat. That's what we know during a phase change. So that basically simply means partial P partial T when the specific volume is constant is equal to dP dt during the saturation. So basically the previous line simply means that pressure is independent of the specific volume. One of the conclusion is the pressure, for instance, is independent of the specific volume. Okay, so because the pressure is independent of the specific volume, then we can change the partial signs into d signs basically. Okay, so that tells us that for liquid vapor phase change, for liquid vapor phase change, we will have, according to this equation here on top, we will have Sg minus Sf is equal to dP over dt during the saturation, obviously we are talking about the phase change, multiplied by Vg minus Vf. Okay, so this equation comes from this Maxwell relation. So let me just add that this was one of the Maxwell relation. So this is a Maxwell relation that we had before, and this equation is basically coming from this Maxwell relation. Okay, so I can just make this equation simpler by transferring this to one side with the same side with the entropy. So let's say I can say dP over dt during saturation is equal to SFG, because Sg minus Sf is SFG, all right, over VFG. Okay, so also one of the equations that we discussed last session said dH is equal to TdS plus VdP. Okay, so this equation is coming from, let me show you where we had it last session. This equation basically. So we had it before, so this equation I'm using that once again. But during a phase change, the pressure doesn't really change. So this dP is equal to 0. So during the phase change, the pressure is constant. So our dP is equal to 0. So basically that means I can get the integral of this equation by saying that dH going from liquid phase to vapor phase from F to G is equal to the integral of TdS also going from saturated liquid to saturated vapor. Alright, and if I get the integral, the left hand side gives me HFG, which is equal to TSFG. Okay, now For the next step, I can combine this equation with this equation. So let me call this one equation 1 star, and also let me call this one 2 star. Now I can just combine these two together. 1 star and 2 star gives me basically dp dt during saturation being equal to, instead of SFG that I have here, I would write HFG over T. So I will have HFG over T, but also here I have a VFG. So all I'm doing in this line, I'm replacing this SFG based on HFG divided by temperature. Okay, so this equation is basically the Clapeyron equation. Now the question is, why this equation, why the Clapeyron equation is important? That's the question. So let me go to the next page. Question. Why the Clapeyron equation is important? Basically, by saying Clapeyron equation, I mean why dp over dt during saturation or during phase change being equal to HFG over TVFG is important. So the reason that this equation is important is because it is giving us the enthalpy of vaporization at a given temperature simply by measuring the slope of the saturation pressure curve. All right, so you know that if we plot the pressure, the saturation pressure as a function of saturation temperature, we will have something like this. So it gives us a Y-shaped plot, and we have all three phases here. So let's say here we have liquid phase. So in this portion we have liquid phase, in this portion we have vapor phase, and here we have solid phase. So let's focus on the line that is separating liquid phase from vapor phase. One thing we can do for any given temperature, let's say for this temperature, on this line, if we draw a tangent line, that slope, which is basically partial P over partial T during the phase change, is a constant value. Like that slope is a fixed number. By the way, so this is for a phase change. You see here in this side we have liquid and here we have vapor. So this line, this blue line, represents the phase change. So the answer to this question is the enthalpy of vaporization, basically HFG, can be obtained by measuring the slope of the saturation curve on a PT, pressure versus temperature diagram, and the specific volume of saturated liquid and saturated vapor at the given temperature. So basically, in summary, if someone asks why this equation, why the Clapeyron equation is important, simply the reason that this is important is because we can obtain this HFG by simply measuring the slope here. So this dp over dt is the slope of this blue line. If we have the slope of that line at a given temperature, then obviously in that temperature we have the T value, and we can obtain the VFG, which is Vg minus Vf. So by doing this math, we can obtain HFG. So that's why this is important. So we should be careful that this Clapeyron equation can be used for any phase change. It doesn't need to be between liquid and vapor. It could be also between solid and vapor, or even between solid and liquid. For any phase change, we can utilize this. So let me just add that the Clapeyron equation can be used for any phase change process. Okay, for instance, solid vapor, which is going to be this portion of the PT plot, or solid liquid. It doesn't only need to be between the liquid phase and the vapor phase. Okay? So the other thing is, whenever we are discussing about low pressures, the specific volume for vapor phase is much greater than the specific volume for the liquid phase. Okay, so at low pressures, Vg is much greater than Vf. So that means VFG can be approximated by simply Vg. So we can easily ignore the Vf part whenever we are at pretty low pressures. And we know that for gas phase, Vg can be obtained based on the ideal gas law, which is RT over P. If you remember, the ideal gas law says PV is equal to RT. That V is the specific volume of the gas phase. So this is what I'm exactly showing here. So that being said, we can say dP over dt during saturation is equal to PHFG over RT squared. Okay, and in case you are wondering where this equation came from, let me show you where it came from. So this equation comes from here. All I'm doing, I'm replacing these HFG with VFG with Vg, which is also equal to RT over P. So this equation is coming from here by replacing VFG with this value, with RT over P. Okay, also I can continue this by saying dP over dt during saturation is equal to HFG over R, okay, dt temperature squared during saturation. All right? So obviously the right hand side is the same. So I have HFG here, P. Where is my pressure? Oh, on the left hand side I have dP over P. This should be pressure. Sorry about that. So the denominator on the left hand side is in fact the pressure. Okay, so I just make it in another color so you know what is happening on the left hand side. So the left hand side says dP over P during saturation is equal to HFG over R dt over temperature squared during saturation. Okay, so this SAT is supposed to be subscript here. So if I continue this equation, I can get the integral to give me ln P2 over P1 is approximately equal to HFG over R, okay, multiplied by 1 over T1 minus 1 over T2 during saturation. And this equation is called the Clapeyron-Clausius equation. Clapeyron-Clausius equation. Okay, so in this equation, we have the ratio of the pressure being equal to the enthalpy of vaporization divided by R multiplied by the inverse of temperature during saturation.